For most of human history, our perspective ended at the horizon. If a hurricane gathered strength over the Atlantic, people on the coast simply had to wait for the wind to arrive. There was no way to watch the planet's systems in real time. This diagram shows the physical wall blocking global communication. Radio signals travel in straight lines, but the Earth is a sphere. Once a signal passes the horizon, it doesn't curve around the globe. It shoots straight into the void of space. We had the Moon, a natural satellite orbiting since the beginning, but it was too distant for relaying the radio traffic of a growing civilization. We needed to build an artificial version, a human-made machine positioned high enough to look over the curve of the Earth. To bridge the oceans, we had to move our infrastructure off the ground and into a permanent position above the atmosphere. In 1945, engineer and writer Arthur C. Clarke calculated the specific mechanics required for this. He proposed that if a machine were placed at a precise altitude, it could stay fixed over one point on Earth, acting as a relay for radio and television. This is geostationary orbit. By matching the satellite's speed to the Earth's rotation, the object appears to hover. From this height, a single satellite can cover an entire hemisphere, bouncing signals back to millions of people at once. Clarke's math was precise, but putting his theory into practice required a rocket capable of reaching speeds of 18,000 miles per hour, a feat that remained impossible for another 12 years. In the mid-1950s, Soviet engineers led by Sergei Korolev adapted military rocket technology to solve the problem of orbital velocity. On October 4, 1957, they launched the R-7 Semyorka. The force of the engines finally accelerated a payload fast enough to fall around the curve of the Earth, rather than crashing back into it. The result was Sputnik 1. It was a simple, polished sphere, roughly 23 inches in diameter. Its 4 antennas did nothing but transmit a steady radio beep, but that sound could be heard by anyone with a shortwave receiver on the ground. Sputnik proved that orbit was reachable. It turned the upper atmosphere into a new high ground, instantly shifting the focus of global power from the surface to the stars. The United States launched Explorer 1 in 1958. This satellite carried sensors that detected the Van Allen radiation belts, demonstrating that these machines could be used to map the physics of space itself. By 1960, Tyros 1 became the first weather satellite. It provided the first consistent photographs of Earth's cloud cover, finally giving meteorologists a way to track storms before they hit land. In 1962, Telstar 1 proved that global television was practical. It enabled the first live transatlant broadcasts, fulfilling the concept Clarke had proposed nearly 2 decades earlier. This technology brought the world into the living room. For the first time, people could watch events unfolding on another continent as they happened. Throughout the 70s and 90s, this infrastructure expanded into navigation. GPS technology, once a classified military tool, was eventually miniaturized until it could fit into a consumer's wristwatch. Within 40 years, satellites moved from being experimental scientific payloads to the silent foundation for the world's communication and navigation networks. While the 1950s sky was empty, the orbit of 2026 is a crowded environment. There are now thousands of active machines circling the planet. This diagram shows the 3 primary tiers of space. Low Earth orbit handles high-speed internet, medium Earth orbit hosts GPS constellations, and geostationary orbit remains the home for massive weather and communication platforms. This density is possible because the satellites themselves have shrunk. These CubeSats are small enough to be held in one hand, allowing companies to launch hundreds of them at once to form a single, massive network. Lower costs and smaller hardware have shifted control of space from a few governments to dozens of commercial enterprises, creating mega constellations that cover every square inch of the planet. By 2026, our reliance on this network is absolute. It handles everything from global internet access and direct-to-phone connectivity to the coordination of disaster relief. Most people will never see a satellite in their lifetime, yet their modern existence depends on them every second. We use this technology to find our way, check the weather, and stay connected without a second thought. Arthur C. Clarke envisioned 3 giant relays. Today, we have a coordinated mesh of thousands of intelligent machines, working together to maintain the constant flow of data required for a global civilization. The history of satellites has reached a point where the digital world and the physical world are no longer separate. We now live on a planet that is managed, monitored, and connected from the high ground of orbit.